suggesting that when we looked at the E1 mechanism, that we would primarily see the trans product over the cis product if given the option. Why do we see the trans over the cis? It's more stable. Yeah. So why was it more stable? It's a steric repulsion. The electron clouds of our largest groups are as far away from each other as physically possible. We can go all the way back to Newman projections and look at all that and fun stuff. Okay, that's what this slide is trying to show with the extra p orbital, so you could see that alignment. Okay? So since since we're talking about stability, let's have a little fun with that. Let's see if we can scare anybody. To perform the elimination, we needed a hydrogen from a neighboring carbon. Okay, so if we take a look at this general reaction, we've got our leaving group, we added heat. Okay, we know we're doing an E1 elimination because formation of an intermediate, we're seeing the carbocation. Okay, so I would tie your 1 to carbocation and 2 to no carbocations. You see a carbocation, you're running the E1 mechanism. So what we just discussed, why does it seem dark in here? That's why it's dark. Okay? We just discussed that we could get 2 possible products, right? Okay, we could get the cis product or the trans product. Which of those 2 is the more likely? The trans, because our large electron groups are as far away from each other as possible. Okay, so we will favor the trans product in our eliminations, okay, if given a choice, okay, which is an important thing to say. If we have a choice, we'll get trans. In E1, we'll always have a choice, so we'll get the trans. Okay. The whole key to this was that we removed a hydrogen from that neighboring carbon, right? We took the electrons out and we made the bond, with double bond, right? Okay. Is there another product? Said another way, is there another hydrogen? There's another product. Okay? So we may be able to go through and say, okay, absolutely the trans forms because it is more stable than the cis, so I expect that. But I now just threw a third product in there. Interestingly enough, I didn't talk about the third product already. So what might you guys be thinking already about the third product? It's not a good one. Why is it not a good product to form? It is not a primary carbocation. The carbocation is still secondary. We're removing the hydrogen from our primary position versus our secondary position. That is not going to have an effect directly on that product.
So it's less groups attached to.
Is this in the cis conformation? It's not in cis or trans. Okay? We have 2 hydrogens at the end there. It's not a cis or trans structure. Okay? So it is not cis or trans. We can't use that. Kind of, not really. You guys actually started already referencing it. This came back from chapter 5. Okay? And we did I didn't like it, but it was in the textbook, and it was actually on the exam. Heat of combustion. The stability of our double bonds. The more substituted our double bond, what happened to the energy of it? It went lower. How many substituents are on this double bond? We only have 1 non-hydrogen substituent attached to the atoms of our double bond. Okay. How many do we have in the trans conformer? There's 1, 2. In the cis, 2. So now I'm going to say all 3 of these are formed. Which one forms in the highest concentration? Next highest. I don't know why I wrote 3 there. Cis, and the last one? The other one. There's the word I was looking for. Thank you, Monica. It is called a terminal alkene. Okay? Alkene because it's a double bond, and terminal just means it's at the end of the structure. Okay? Not quite dead, but kind of that idea. So when we look at our products, we can predict something about how they go through and form. It's the location of that double bond, and it's the number of substituents on it. Okay? The lower energy our product is, that's going to help us get a lower activation barrier, and this is ultimately coming out of something known as the Hammond postulate, which we already talked about. The transition state energy is closest to what? The highest energy reactant or product. Okay? So if it's an endothermic reaction, the transition state should be closest to the product. If it's an exothermic, reactants. What would we expect of the elimination reaction? Which should be higher in energy, reactants or products? Why should the products be higher in energy? Nope. What do you mean formation of a pi bond? Why are pi bonds higher in energy than sigma bonds? Higher in energy means they're less stable. They're using p orbitals, which are higher in energy than s orbitals, all the way back to our stupid hybridization theory. Okay? So our pi bond is higher in energy. When we do an elimination reaction, it is an endothermic reaction. Didn't we talk about always having exothermic reactions? Yes, to get this reaction to occur, we have to adjust certain dynamics to force the elimination to occur. One is adding enough heat that we clear the activation barrier. That's still not going to favor our elimination. We're still going to get a lot of our starting material here. So what we can do is come up with experimental methods to remove one of those species. We can remove the product, thereby preventing the reverse reaction in our equilibrium, which means we constantly make product. What did we do on Monday, guys? A distillation, which was an elimination reaction where we isolated the alkene left behind our starting material in the distillation pot. Okay? Our experiment is designed to allow the elimination to occur. What else can we do? We can try to up the energy of our starting material. Okay? If we can make that more reactive, add other species in there to advance its reactivity, that's going to help balance that out as well. Okay? So, energy diagram. Okay? On our energy diagram, what do we have shown already? We have the reactant, we have the intermediate. Would we expect the intermediate to be so much higher than the reactant?
Yes.
Why? It's charged. Okay? It's not necessarily adding energy. We'll always have to add energy, every single time. Okay? But we're forming a charged intermediate. So now the question is, where should we put the product? It should be lower than the intermediate because it's not charged. Where should it be relative to the reactant? It should be above the reactant because we're looking at a pi bond versus no pi bond. So we could theoretically just drop in an arbitrary line for our product, and we could look at our energy diagram. Okay? What's going to cause one product to be formed greater than another? It's going to have to do with the energy of our product. What happens if we drop the energy of the product? It's lower in energy, but just dropping in energy doesn't speed up that product formation. By dropping in energy, what happens to the energy of the transition state? That's going to go down significantly because our transition state is closer in energy to, it's actually closer in this case to our intermediate. Okay? So we'll see that drop ever so slightly, actually, not a whole lot, but we'll see a little bit of a drop there. So why on earth then would we see the product of lower energy be our favorable one? Run the reverse reaction. What happens when we run the reverse reaction between our red product and our blue product? Which one goes in reverse quicker? Why the red? Lower activation energy. Which means in our standard state, we're going to get an equilibrium going back and forth between all of these. Okay? The red goes back to form the intermediate. Now what happens? The intermediate can go through to form the blue product. Is that reaction as reversible as the red? Which means it stays there. So we're relying on an equilibrium dynamic to help push our reaction along. So it was an incorrect reference to the Hammond postulate. I apologize. Apostulize. Okay. If we go through and add some energy arrows to the top of this, we've got 3 products here. 4 are 3 possible products. Which one's which? C is the top, followed by A, followed by B. Okay. When we run the reaction, oh, that was horribly drawn. You didn't mean Christmas. Our transition state energy will drop ever so slightly for that second step, but not a whole lot. Okay? And that's because our transition state is closer in energy to our intermediate. What's really going to drive the high formation of our product of B is because C and A are going to be very easily reversible. Why are they reversible? Because those species are higher in energy. Okay? How can we explain them being higher in energy? Okay? That gets a little bit, yeah, let's actually bring this in now before we even do that. Heat of hydration, what does heat of hydration mean? Exactly right. That was, you may laugh, but that's it. We start with an alkene, we go to an alkane. That is our hydration. What did we add? Hydrogen, that's it. Okay? Or it's technically heat of hydrogenation. Okay? So what happens? It's the energy released when I go from my alkene. So everything up here was an alkene down to my alkane. Which of those gives us my highest heat of hydrogenation? C, because it starts at the highest energy state. Okay? So we can quantify energy stability by looking at heats of hydrogenation. That hydration is bothering me. Sorry, I need to fix that. Very similar to what we did earlier with combustion. Same idea. Okay? It's a relatively easy question to answer once you have an energy diagram. If you're just given the structures and asked which has the highest heat of hydrogenation, it becomes much trickier to analyze. The higher heat of hydrogenation is going to come from the least stable species because it is higher in energy relative to our alkane. Kind of, sort of? Yes.
So, is the alkane level with the reactant?
Ignore where the alkane level is relative to the reactant.
Just
That's not. Yeah, that's just how I put it there. Okay. Theoretically, it should be lower.
It's just going to be products.
Okay. So the other thing I like to go through and do is look something like this. We can look at tetrasubstituted, trisubstituted, disubstituted, and monosubstituted. A lot of students seem to be confusing this. And they'll take a look at, let's say, that middle structure, and they'll say that the double bond is disubstituted because there's 2 carbons. Okay. Those are the carbons of the double bond. They are not substituents on the double bond. When we're referencing substitution patterns, we are looking at the atoms attached to the carbons of the double bond. So in that center or that boxed example, I will ignore those carbons and I will look at the substituents around it. Okay. There's 4 things attached. If I look at all of them, how many things are attached? 4 things. There will always be 4 things because octet rule. Okay. There has to be 4 things. Okay. So how do we decide this substitution pattern then? Okay. Our substituents are referring to anything other than hydrogen. Hydrogen is everywhere, so we will ignore hydrogen in our counting of substituents. So when we go through and look at our boxed in one, there's really only 3 substituents that are non-hydrogen. That is trisubstituted. Okay. Are there further categories that we could drop in here? If we take a look at the disubstituted, is there another way we could do the disubstituted? We have a cis-trans issue popping up, so I drew the trans underneath. Okay. Which is more stable, Trans disubstituted or cis disubstituted? Trans disubstituted. So it's recognizing those patterns and identifying and ranking their energies. That's going to allow you to predict which product is going to become more favored. So when we go through, and there's all your circles for all of those. So in an elimination reaction, if given the choice, what do we make? We can get more specific than trans. The most substituted trans alkene. Or said another way, the lowest energy alkene. That's it. That's what you're doing. Lowest energy alkene, that's what you make. Okay? This was then put into words, and we end up with Zaitsev's rule. Okay? Zaitsev is saying we just form the lowest energy double bond. Okay? So our more substituted double bond.
So the tetrasubstituted is the most stable.
Is our most stable. Yep. Right. Anybody notice something kind of unsettling with the slide? If we look at the bottom, there's an exception. Okay. We will talk about this a lot more in second semester. There is another product referred to out there. It's known as the Hoffman product. Okay. Why do we end up naming it the Hoffman product? He's the one that discovered it, and it was so drastically different from the Zaitsev product that he got to rubber stamp his name on top of it. Rubber stamp's a bit overzealous. He actually did some other chemistry associated with it too. For first semester, our exceptions only for E2, so everything we've talked about so far is E1, but in an E2 mechanism, okay, if our hydrogen is sterically hindered and we have, or sorry, our leaving group is sterically hindered, old slides. If our leaving group is sterically hindered and we use a sterically hindered base. What does sterically hindered mean? A lot of electrons. The more electrons there are, the more likely you end up seeing the Hoffman product come out of this, okay, in an elimination. It does require certain conditions. We need a very sterically hindered base. So again, sterically hindered, okay, and it needs to be the E2 elimination. Okay, it has to be done E2. Okay. So there's our structure. Which product is favored? See, so we have an elimination reaction here. Substitution, elimination, and elimination. Are any of those invalid structures? No. Which one is better is then going to come from the context of other clues that you need to find in your reaction. At this point, we haven't discussed our clues for substitution for elimination, so don't stress about the substitution one. We do have the clues to decide which of those elimination products is correct. Which one? The middle one is our most correct because we are a tetrasubstituted or tetrasub double bond. Okay. What about the last one? Can you eliminate that outright?
Yeah.
Why?
Because the charge was on the right, and you actually did you just flip it a little bit.
Yeah, there's our issue. You can't just eliminate that one outright. I know you want to because you're saying, oh, the double bond happened on the wrong carbon. All we did was rotate the structure. Okay, so be careful eliminating answers just because it looks like the chemistry has happened somewhere else. We can take the structure and rotate it, flip it, turn it on its head. It can hide that answer. Okay, so that last one is wrong because it's a terminal alkene or disubstituted. The first one was wrong because trisubstituted. Okay. One of the things that I like to do to help kind of think about how these things are reactive, if I go lower in energy, that means less reactive. So how does the alkene react? What is reactive about the alkene? The pi bond. What has to happen for the pi bond to react? What do the electrons need to do? Yes? What do the electrons need to do to react with something? They must share where? outside the structure. So those electrons must do what? Leave. So as it tries to leave that direction, what does it encounter? A carbon. What does carbon have a bunch of? What happens? Gets scared and goes back. How about the other direction? Same thing, scared and comes back. The other direction? Same thing, scared and comes back. That direction? Still encounters something, but it's the smallest something we could possibly put there. It has one out, okay? One reactive pathway. What happens with the tetrasubstituted? 0 reactive pathways. Last one? 2 reactive pathways. Okay. For anybody watching the video at home, that is technically untrue, because that's not how a double bond reacts. But as a rough superficial analysis, it works beautifully. Okay? Yes.
Third one again? You said you flipped it?
Third one is a valid structure. Okay? It is a valid product. Most people were eliminating it because they're saying it's not this structure. What is the relationship between those two structures? They're the same thing. All we did was flip the structure over. Okay? So we can't eliminate it because it's putting the double bond in the wrong place. It's a perfectly valid double bond to have. It just happens to be a higher energy double bond. Okay? Questions about that? Where are we? 54. Oh, awesome. Elimination repercussions. Okay? What is the relationship between the two starting materials? So we'll help you out. Erase all that. What is the relationship? They are diastereomers. Okay? Is that going to become problematic with this? Yes. Okay. We did a similar reaction with the E1. Okay? In fact, I think we start with that same structure, except in the E1, we ended up not showing the diastereomer. Okay, why not? In the very first step of the E1 elimination, what happens? Leaving group leaves, and I have a carbocation. Okay, what would my relationship now be? Enantiomers, their chemistry is going to be roughly the same. Okay, so I don't need to stress about it. And that's why we get two products. What happens when we do the E2 elimination? We break and make. So the bond between the carbon and the hydrogen must be broken at the same time as the bond between the carbon and the leaving group breaks. Okay? So those are the arrows we must use. What would be the result of that? We now have the double bond. What happens to the arrangement of the phenyl groups and the methyl relative to each other? They stay the same because everything's happening at the exact same instant. They cannot change locations, which means when I set up my elimination, whenever it happens, whatever conformation I'm in, I must be maintained in that conformation. And yes, this may look weird, and technically is, okay, but if we now take that resulting structure and flatten it out, what kind of product do we get? We'd get the trans. Our two largest groups, our phenols, would be on opposite sides. Okay.
Would this then be helpful to help prevent the chirality changing for RNS?
So, good question on RNS. When we brought in two mechanisms, the two type before in our SN2, we had inversion of stereochemistry, right? Mm-hmm. Do we need to worry about stereochemistry in our product?
No.
Not really, because there is no chiral atom. Do we have to be concerned about cis-trans isomerism? Yes. Okay. That is going to become important. And when we look at this product, we get the trans. Well, that's what we got in the elimination. Right, the elimination is going to get you the trans, okay? Or the E1 elimination will get you the trans. What happens if we went and did this same substrate, or our enantiomer of our substrate, okay? And now we do that same elimination. If we do it under E1 conditions, what product do we get? The same one, the trans, under E1 conditions. Our E1 is always going to adjust to get us to that trans conformation. what happens in the E2? We have to break and make the bond at the exact same instant, which means what happens to the relative locations of those groups? They stay the same. They cannot move. What does that mean happens when I flatten the structure out? I have the cis product. But in the E1, I never get the cis. I get the trans. It's really hard to get the cis in the E1. Why do I now get the trans, or sorry, the cis in the E2? No time for rotation. But I got the trans up here. What's the issue? Based on the starting material, based on when we do the elimination. Well, what if I had rotated about the sigma bond before I did the elimination with that first structure? Couldn't I have rotated it to get it into that cis conformation? The hydrogen and the bromine are our key. When we go through to do our substitution reaction, where did our nucleophile come in from? The backside. Why? Less steric hindrance. The leaving group would block it. What if I did a rotation about my sigma bond? Okay, for this, let's do it actually for the top one. So there's my phenyl, there's my P8, my bromine. Doing a rotation to get the hydrogen now down. If I do that, I get the CH3 going away. And I get the phenyl coming at. Everybody okay with that? If I did the elimination now, what product would I expect to see? I would expect the cis. Okay. But if I start with this starting material, I never get the cis under E2 conditions. Never happens. Okay. With this substrate, I only get the trans. Why is that cis not physically possible? The phenyl groups is our steric hindrance. Okay? So in this case, we want to say, okay, you're making the argument. That's fine. Okay? So let's go through and switch it and look at the other one. Because the other one produced the cis. And we said cis is horrible. We should never form cis. So let's do a rotation with that one. There's our phenyl. We'll do our rotation, bring the hydrogen down. We did that rotation, we should end up with CH3 phenyl, right? When we do our elimination, what product would we expect? Trans. Everything about this screams trans, right? So now given the choice, which product should we form? We should form the trans. And what I'm saying is that when we run this substrate in an elimination reaction, the trans never forms. None of it. Don't get it. Why? Okay. This goes back to how the reaction works. Under SN2 dynamics, we have a backside attack. Okay. What is the attacking atom in this case? The hydrogen. Where is the attacking? It needs to be attacking the backside of the leaving group bond. Where is the backside of that carbon-bromine leaving group? In this configuration, are the electrons from that carbon-hydrogen going into the backside? No, they're going into the same side. What happens? Electron-electron repulsion, the elimination doesn't occur. What happens if we rotate it back to the way the textbook actually drew this? Where's the backside of our carbon-bromine leaving group? Now when we do the elimination, we're eliminating into that backside. We can do the elimination. Now the elimination occurs. Okay. For those of you going, holy crap, it's just a bunch of arrows and lines. You're having a hard time visualizing the three-dimensional models. That's fine. Get out some model kits and align this to see that you can verify this. The next big issue is that when we do the elimination, the E2 elimination, you will almost always see this negatively charged species floating around there. What can a negatively charged species do? It could act as a nucleophile or a base. In this case, because we are told we're doing an elimination, it is acting as a base. Those are a big source of electrons, right? If we look at the nice drawing of it, when that base comes in, all it sees is the positive hydrogen. Right? And we could even make the argument it sees the positive carbon, so it's being sucked to that side. What happens if we did that rotation? Where would the base then be coming in? What would it see? It sees the leaving group, okay, which would then repel it the other direction, and it can't get in to react with the hydrogen. Okay. This particular arrangement of your leaving group and the acidic hydrogen has a very special name. Okay. That special name, let's see, did I draw a nice picture of it? Oh, I didn't, but the textbook did. Becomes a little bit more obvious if we say rotate the structure into a Newman projection. Yay! Newman projections. We draw out the Newman projection. What do we end up seeing? There's our bromine as our leaving group and our hydrogen that's getting removed. They're located anti to each other. Okay? To do the elimination, the E2 elimination, the 2 type, we must be in this anti-conformation. Once we are locked into that anti-conformation, the arrangement of the groups in the Newman projection are now locked into position. That ends up dictating the arrangement of our groups, either cis or trans. What if there is no cis-trans? There's a good answer. Don't worry about the anti-conformation. You look at your products and you see cis-trans as a possibility, you need to be thinking about this anti-arrangement. Why does this become more difficult? When we looked at that question to begin with, where's the Newman projection? It's not shown. You would have to show that Newman projection. This is why we show you how to draw them, so that you can take this and you can convert it to a Newman projection to see the proper alignment. Once we're in the proper alignment, you can then do the elimination to draw a new Newman projection of the product and then rotate it back to our normal view. Okay? Those of you being like, that's way too hard, okay? Good luck. That's what you need to do. Okay? We go through dealing with those structures and those manipulations so that you have the practice doing it enough on paper by now that you don't have to draw it out. You can see it already in your mind's eye. Isn't the mind a lovely place? Okay? If you can't see it, that's fine. Draw it every single time. Make sure that you maintain your chemistry around it. Remember I asked you to take line angle structures and turn them into Newman projections and make sure they're correct? This is why. You can't just draw an arbitrary Newman projection. The Newman projection has to match the stereochemistry of the starting structure. Kind of makes sense?
So the slide before, both of those are valid. Because
Both of these are valid E2 eliminations. The reason why we end up with cis and trans as products is because our starting materials are different. Okay? If we compare those two structures, they have different chiralities, come on pen, about that carbon.
they're both anti as well, so.
And they're both in that anti-conformation, allowing for us to do that double bond. So you must be anti. Okay, why does this become problematic? What was our previous slide talking about? Form the most stable double bond. Is this the most stable double bond? No. When do we form the most stable double bond? When? Our E1 eliminations. As soon as we hit E2, we now have to be much more careful when we go through and evaluate our products. We do still want to form the most stable double bond, but that is possible. Okay? It is not possible to make the trans double bond with our bottom starting material. Okay? So you have to be a lot more careful when it comes to your E2 eliminations to ensure you're aligning those things properly. Okay. Questions? Okay. So there's some nice pictures. You can see some rotations and all that fun stuff. Why is it not a problem for the E1? We have the formation of a carbocation. So when we look at the relevant or comparable step in the E1, what do we have? There's our hydrogen. What do we have in the back? A carbocation. When we do the elimination, even in the E1, what's happening? The hydrogen is still in the plane of the p orbital, but I can do a rotation to put that hydrogen either above or below when I do my reaction. Okay? Because in the intermediate, I have a sigma bond connecting the carbon with the hydrogen and the carbon with the cation. I can do a free rotation there, which means whichever one of those generates the more stable product is going to be my product. That's why I'm getting the trans. Okay, in the E1. The E2, there's only one Newman projection that works. There's only one case where I get the alignment of my hydrogen lining up with the leaving group, and that's because the leaving group is not left yet. I don't have a carbocation where I have two sides. Kind of, sort of?
So you can rotate for...
So in an E1, we can do all sorts of rotations to generate our most stable product. That's where we get trans preferentially. With the E2, we have to make sure that we're in the proper alignment first, then we do the elimination. Whatever product we get is the product we get. We're stuck with it. If you feel like your mind's blown on that, that's fine. That's typically, I think, how the E2 elimination works. Okay? It is a very tricky one to work with. Okay? With our E2, what happens if we have two hydrogens that we could potentially pull off? Okay. Well, that means there's two hydrogens to choose from. I can still do a rotation about the sigma bond before I do the elimination. In one case, when I do the elimination, I'll be removing one hydrogen. In the other case, I'll be removing the other hydrogen, which means two products. One of those products will be the cis, one of those products will be trans. If I'm given the option of two products, what's my option? Always the lowest energy. Okay? So with the E2, you just have to look. Okay? Is there only one hydrogen I have access to? I need to be very careful with the choice of stereochemistry of my products. If I'm given two options, draw the trans, move on. Okay? The trans will be more favorable. Okay? And that's because there are now two options to choose from. They are going to be pulling different hydrogens, though. Okay? Kind of makes sense? So our big one is that can result in two products. Okay, Chapter 8. In Chapter 8, you're really given one condition. You are told there's SN1, E1, SN2, and E2. Those are the mechanisms. Do them. So I say, here's your starting material. I want you to do an SN1. Do an SN1. Okay? If you've already started to work into Chapter 9, you're like, but this shouldn't do SN1. I don't care. It says do SN1. Do SN1. Okay? Or if you look at it and say, yeah, I think that's better to do an SN2. I don't care. I said SN1. Do it. Okay? That's what Chapter 8 is telling you to do. Okay? Given these conditions, I am telling you to do this. Do it. Okay? It is setting you up with the practice for getting through how you move from reactants to products given a particular mechanism. What happens when you move to Chapter 9? You are not told what to do. You are given the starting material, and you're expected to predict the product. Okay? Well, does that mean you're getting a substitution product? Maybe. Does that mean you're getting an elimination? Maybe. Does that mean you need to be anti-periplanar or anti-conformation? Maybe. Okay? You have to look at the conditions and say, does that favor substitution? Does that favor elimination? Once you've differentiated that, then what do you need to figure out? Let's say our reaction favors substitution. Then what do you have to do? Is it SN1 or is it SN2? Or does it matter? How would you know it matters? Number of products, stereochemistry. If you look at your answer choices and then you see stereochemistry involved, you should be concerned about the type of mechanism. Okay? What if we asked optical activity? What is that referencing? That is referencing chirality. When would we have a optically active product? SN2. When would we have an optically inactive product? SN1. How do we know that? It comes back to the complications of each of those mechanisms. The SN1 generated 2 products, okay? Because our new atom could come in from top or bottom of our cation. Okay? SN2 can only come in from one direction, which means we end up with an optically pure sample, relatively at least. Okay? So there's multiple ways to test at each of those applications, and all of those multiple ways take advantage of the stuff we talked about at the beginning of the semester. Okay? To predict which mechanism to do, what do we have to use? Everything we talked about at the beginning of the semester. Okay? After that, you are hoping the best you can to memorize the crap out of it and see what you can get through. Okay? If you think it's substitution, do the substitution. Don't worry about stereochemistry. Eliminate answers, whittle it down, put something in. Okay? Prove that you do know some parts. You do know some parts. You may not know the perfect answer, but you do know parts of it. Establish those parts. So, mechanism considerations. Okay? Here's a fun one that we didn't talk about. When do we see carbocations? E1, we just talked about that. E1 gets us a carbocation and SN1. So I would change my memorization on carbocations because that's saying I have to remember 2 things. I have to remember E1 and SN1. What can I change that to? If it's 1, I need to know carbocations. Okay? What's the issue with carbocations? They can rearrange. The instant you draw a carbocation, the very next thing is not what's my product, it's do a rearrangement. When should you actually do that rearrangement? If you make it more stable. What's a more stable carbocation? Tertiary. What's else? Secondary is less stable than tertiary. Resonance. Okay, so you need to be thinking resonance and tertiary versus secondary versus primary whenever you see a carbocation. Acid-base steps, there's leveling effects. You've got to watch out for those leveling effects. Not as big a deal. If you're in a strongly basic environment, at no point should you be showing me a positive atom. Why?
There's electrons everywhere.
There are electrons everywhere in a strongly basic environment. If you're in a strongly acidic environment, you should never show me a negative because there are protons everywhere. So be very careful when you go through and draw a mechanism to make sure that you don't tag those high negatives or high positives. Intramolecular reactions. Intra meaning within. Do not do them. All right, that's kind of our bottom line for this unit right now. You can pretty much just say it doesn't happen. They are very, very difficult to happen. Okay? One way to think about it, okay, if I'm going to do an intramolecular reaction where I take my index finger and I touch that to any other place, be nice, on my body, where is a valid connection for my index finger? Forehead, my nose. How about the second knuckle in my finger? Can I do that? Well, let's try the other way. Okay, it doesn't work. Why? The distance is too short. It can't bend and force back. Most intramolecular reactions that you're trying to do something like that. You are trying to connect the tip of your finger to your first knuckle. Okay? It doesn't work very well. Okay? Please don't try it. Okay? So, as far as what things will happen here, because we did kind of chase down some acid-base stuff. How are you guys doing with carbocation rearrangements? Because that already happened in chapter 7. So in theory, you're okay with that? Should I be doing review slides on carbocations? Yes. Okay. So I will try and put up... Ooh, I didn't do a very good job on that. I'll try and make some better slides for carbocation rearrangements so you can see what's happening here. Okay. This is a classic example of carbocation rearrangements. Okay? Acid-base mechanistic steps that are bad, I'm going to skip over that. We'll talk about that. Maybe we'll talk about that Monday, but I won't put any questions on the exam directly on that. Okay? Intramolecular, same deal. Won't worry about it on the exam. This is a case where it's okay. Why? Because I told you to do it. That's why. Okay? I know it kind of sucks. And if you don't like me telling you to do it, it's because the chemistry told you to do it. That's why. Okay? So where I really want to focus that online video is going to be starting with this, looking at the substrate, leaving group, nucleophile and or base, and solvent. So that's this next sequence of slides. Substrate classifications, leaving group abilities, a bunch of rules, solvent classifications. We already talked about this in Unit 1, but how do those solvents then play roles in deciding your mechanisms? Okay? And then nucleophiles. The big issue with nucleophiles, there's a bunch of different rankings here. The big red box is because you need to know those. The harder ones, maybe one question on. Okay? Big issue with nucleophiles, though. Nucleophile is electron donor. What is base? Electron donor. What's the difference between electron donor and electron donor? Not a whole lot. Nucleophile is very important for substitution. It is horrible for elimination. Base, pretty important for elimination, and it is horrible for substitution. Yet they're both defined the exact same way. Okay? So this slide looks at that difference between them and helps you kind of look at the structure and say, is it a nucleophile or is it a base? After that, the rest of the slides, all the way out, which is something like 15 slides, are just review, looking at the different mechanisms and trying to organize them and decide which mechanism you're doing. Okay? So that's what we'll focus Monday on. I'll try and give you some more practice problems to get through that. Work on the homework. As far as I know, the homework's valid all the way through. Okay? You might see some on intramolecular acid-base stuff. Just do that one question, you'll be okay. All right?